Friends, today we shall study about the force convection. Force convection. Then in that we will study about a flow over a flat plate. Velocity boundary layer. Whenever a fluid at velocity u infinity flows over a stationary flat plate, a thin layer in the vicinity of the plate will be retarded due to skin friction between the plate and the fluid. The particles which make contact with the plate will stick to the plate and will have zero velocity. At sufficient distances far away from the sufficiently far away in the plate, it is observed that again the fluid particles are moving with the same stream velocity u infinity. This is because when you move away from the plate, the effect of skin friction is reduced. The fluid particles which are in contact with the plate will have zero velocity, and the adjoining fluid particles or fluid layers moving above this bottommost layer will get retarded due to interaction between a slower moving layer and a faster moving layer at the top, leading to a viscous shear force. This viscous shear force is formed due to velocity gradient and the viscosity of the fluid. At any location x from the plate, one can locate a point along y direction, y equal to delta x, where velocity of the fluid particle has reached nearly the free stream velocity. Nearly reach the free stream velocity. The locus of all such points where the u is equal to 0.99 times of u infinity is called as velocity boundary layer. Thus, the velocity boundary layer divides the flow into two regions. The flow within the boundary layer, where the velocity gradients do exist and effect of viscous forces are significant. The flow outside the boundary layer, where all the fluid particles are moving with same stream velocity u infinity, and there is absence of velocity gradient, and viscous forces are negligible. From the velocity diagram, from this velocity boundary layer, it is clearly seen that two regions, laminar region and a turbulent region. The type of flow within this boundary layer is determined by a Reynolds number. Reynolds number for the flow over a flat plate is defined as Rex equal to u naught x by nu, where u naught equal to free stream velocity, x is equal to distance from the leading edge, nu equal to kinematic viscosity of the fluid. Up to some distance from the leading edge, the flow remains orderly and the fluid particles will move along streamlines, and the flow is said to be laminar. Then when the critical Reynolds number is exceeded, the critical Reynolds number for the flow over a flat plate is 5 into 10 raised to 5. Whenever the critical Reynolds number is exceeded, the small disturbances in the flow will get amplified and fluid fluctuations will develop, causing the intense mixing of the fluid layers. This characterizes the end of the laminar layer and beginning of the turbulent boundary layer. The velocity profile in the laminar boundary layer is different from the velocity profile in the turbulent boundary layer. Velocity profile in the boundary layer shows that velocity of the fluid particles is a function of both x and y. It varies along both x and y direction. It is function of x and y. This is all about the velocity boundary layer. Now we shall go to the thermal boundary layer. So whenever a fluid at velocity u infinity and temperature T infinity flows over a stationary flat plate, a thermal boundary layer is developed along with a velocity boundary layer. The fluid particles that make contact with the plate will come into thermal equilibrium with the plate and will attain the same temperature as the plate, that is Tw. These fluid particles will give heat to the adjacent fluid particles above by conduction, and a temperature gradient is developed. The temperature gradient developed goes on decreasing as we move away from the bottom, and at sufficient distances away from the plate, it is observed that the fluid has attained the same temperature as free stream temperature T infinity. Thus, if you define a non-dimensional temperature theta as theta xy is equal to Txy minus Tw by T infinity minus Tw, where Txy is the local temperature in the fluid, temperature of the fluid particle in the fluid, then at the wall surface, temperature of the fluid particles is equal to Tw, and theta xy becomes 0. At sufficient distances away from the plate, Txy, temperature of the fluid particles, will be equal to T infinity, then theta xy equal to 1. Thus, the temperature of the fluid particles varies from Tw to T infinity along y direction, or in other words, theta varies from 0 to 1. At any location x from the leading edge of the plate, one can locate a point at a distance y equal to delta Tx measured along y direction, where theta equal to 0.99. That is where the fluid temperature has nearly reached the stream temperature T infinity. The locus of all such points where theta equal to 0.99 is called as thermal boundary layer. The temperature profile in the thermal boundary layer is also shown here. It is also a function of both x and y. Now, Prandtl number. When the fluid at velocity u infinity and temperature T infinity flows over a stationary plate, both velocity boundary layer and thermal boundary layer are formed. The relative thickness of these boundary layers, which is more thicker than which is more thick and which is more thinner than that is decided by a Prandtl number. For gases, Prandtl number equal to 1, velocity boundary layer equal to thermal boundary layer. For liquid metals, Prandtl number is less than or equal to 1. Therefore, thermal boundary layer thickness is greater than velocity boundary layer. Thermal boundary layer thickness is thicker than the velocity boundary layer thickness. For fluids having PR, Prandtl number is greater than 1 or equal to 1. Thermal boundary layer thickness is less than velocity boundary layer thickness. This is all about the velocity boundary layer. So we will continue in the next class.